Hello students, in the earlier lecture we have seen preliminaries for the DSP, simple use of the DSP also. Now let's see how the DSP works for various aspects. So in order to study the DSP, the very first thing is you should know what is signal, because it is highly depending on the nature of the signal. A signal is defined as any physical quantity that varies with time, space, or any other independent variable or variables. So to understand this mathematically, a signal is a function of one or more independent variables. Like in the example 1, s of t. This is what one of the signal. It is depending on the variable t. Similarly, in the second example, equation is given 3x plus 2xy, means based on the values of x and y, s, that is the signal is depending. So this is what the mathematical, we can say, the definition for the signal, and this is what the general one. Which are the different types of signal we can observe? Like the natural signal, when we say ECG, it is nothing but electrocardiogram signal. So it is the signal that provides information about the condition of the patient's heart. So here actually we are dealing up with the some of the waveforms which are being monitored based on their heights, like the up and downs, and these waveforms are simply called as a ECG. So based on their amplitude and the nature of variation, these waveforms are simply monitored and will give the information about the condition of the heart. Similarly, there is one more signal that is called as EEG. EEG means electroencephalogram. This signal provides information about the activity of the brain, whether the brain is working sharply or not, or whether it is slow down. All these things will be monitored with the help of the EEG signal. Now let's see the which are the other format of the signal, like real and complex valued signal. So from this first example, we can observe that there is no complex term, means the term in terms of the J is mentioned. So that's why this is nothing but the real valued signal. The second signal term is mentioned in terms of the J. So this is what this entire signal carries, the term in terms of the real as well as the complex. But in order to differentiate whether it is real or complex, then definitely this is with the complex valued signal. This example is taken from the Prokis itself. Now the next part is the deterministic versus random signal. So which signal we need to call as a deterministic? So from this entire description you can just check out, mathematical analysis and processing of signals requires the availability of a mathematical description for the signal itself. This mathematical description, often referred to as the signal model, leads to another important classification of the signal. Any signal that can be uniquely described by an explicit mathematical expression, a table or table of data, or a well-defined rule is called deterministic. Means if the signal is bounded with respect to the mathematical model, it is deterministic. This term is used to emphasize the fact that all past, present, and future values of the signal are known precisely without any uncertainty. Uncertainty means it is nothing but the probability of occurrence, in short. So uncertainty and the probability, these are having the, we can say, the inverse proportion. So in many practical applications, however, there are signals that either cannot be described to any reasonable degree of accuracy by explicit mathematical formula. So like whatever we just mentioned, if it is not bounded with respect to the formula or the mathematical model, that is nothing but the random signal. Such description is too complicated to be of any practical use. The lack of such a relationship implies that such signals evolve in time in an unpredictable manner. We have referred to this signal as random. So these are nothing but the random signal. This is all about some of the signals. We We may go for additional signals also over here. Now let's see what exactly the use of all these signals to the physical device which we use to call as a system. So this is what the system. System may also be defined as a physical device that performs an operation on a signal. It's any any device that performs operation on a signal, that is nothing but in short system. For example, a filter used to reduce the noise and interference up to a desired signal is called a system. So filter will be acting as a system over here. Similarly, device which used to calculate the values of or the nature of all these ECG, that device itself is called as a system. So this is equally applicable for any embedded systems also. Like this embedded system means it is nothing but the system which is designed for doing a specific application and with respect to the specific controls. So that is what system means. So thank you everyone. In the next lecture we are going to see which are the different basic elements of the DSP system, how the DSP system is formed, what is its objective, which are the different blocks that the DSP constitutes, and how all these blocks will give a faithful output that is called as a analog to digital conversion or analog to discrete signal conversion. So thank you everyone. Thank you very much.